10 factors affecting solar power generation. Number 1. Solar resource availability. The electricity output of a solar power plant, given a fixed installed capacity, is directly influenced by solar radiation. Stronger solar irradiance means higher electricity generation. However, the intensity and spectrum of solar radiation vary with weather conditions, making it a dynamic factor. Number 2. Solar panel installation angle. In the same region, different installation angles capture different levels of solar radiation. Adjusting the tilt angle of the solar panels using fixed adjustable racks or incorporating solar tracking systems can significantly boost energy capture and efficiency. Number 3. Inverter sizing ratio. The inverter sizing ratio refers to the ratio between the inverter's rated power and the solar panel capacity it serves. Since energy losses occur as power flows from the modules to the inverter, and inverters rarely operate at full capacity, it's recommended that the PV module capacity slightly exceeds the inverter's rating. An optimal design ratio in high solar resource areas is generally between 1.2:1 and 1.3:1. Number 4. String configuration and matching. Differences in current among series-connected solar panels can lead to current mismatch losses, while voltage mismatch losses may occur in parallel configurations. Ideally, current mismatch losses in a string should not exceed 2%. Number 5. Shading. Shading, whether from dust, snow, vegetation, nearby structures, or even other solar panels, reduces the radiation reaching the modules, limits heat dissipation, and lowers output power. In severe cases, shading can create hot spots that damage the solar panels. Number 6. Temperature characteristics. As the temperature of crystalline silicon cells rises, their open circuit voltage decreases. Between 20 degrees Celsius and 100 degrees Celsius, each 1 degrees Celsius increase in cell temperature typically reduces voltage by about 2 millivolts. While current increases slightly with temperature, the overall power output decreases. Typical power temperature coefficient is -0.35% per degree, meaning power drops by 0.35% for every degree above the nominal temperature. Number 7. Solar panel degradation. Over time, solar panels experience a gradual decline in power output. This degradation can be categorized into destructive degradation, initial light-induced degradation, and natural aging. For example, polycrystalline modules typically degrade by less than 0.5% in the first year and 3.2% over 2 years. Monocrystalline modules degrade slightly faster, with rates under 3.0% in the first year and 4.2% within 2 years. Number 8. Equipment reliability. Equipment failures, particularly those in critical components like inverters, can directly halt energy production, leading to significant losses. Even minor performance issues in operational equipment can result in lower than expected power output. Number 9. Maintenance. Regular maintenance and inspections are vital for maximizing efficiency. Thoughtful scheduling and efficient execution of these activities can minimize downtime and energy losses due to routine servicing. Number 10. Grid curtailment. In some regions, grid operators may impose power curtailments on solar power plants due to limited grid capacity or dispatching requirements. Such limitations can restrict the plant from operating at full capacity. Conclusion: several factors influence the power output of a solar plant, including solar resource availability, solar panel installation angle, inverter capacity, string configuration, shading, temperature characteristics, module degradation, equipment reliability, maintenance practices, and grid curtailment. Understanding and optimizing these factors can unlock the full potential of solar energy systems, ensuring maximum efficiency and returns.